Okay, it's 4:01. So let me start anyhow. So welcome to optimization method for civil engineering, week 8 discussion. And today we'll be discussing multimodal genetic algorithm, and we'll try to uh, solve one or two iterations, time permitting, of a real coded genetic algorithm. So last class I had shown binary coded genetic algorithm. We will this time try to go for the real coded. I am audible, right?
Yes, sir.
Oh, thank you. Thank you. So, what were the steps that we did in the binary coded genetic algorithm? So, step one, often even sir did not include this when he was describing the steps, but I personally feel like I should include this because based on the encoding algorithm or big encoding formulation, we decide some kind of precision for our solution, and using that we decide the length of the string of that binary chromosome or string. So that is step one. Then we generate initial population and we calculate the fitness of all the members of this population. And there is a elitism operation which preserves the fittest solution to be directly transported to the next generation. And then our standard selection, crossover, and mutation. So the member of this population, which has been chosen by elitism, will not be going through the selection, crossover, and mutation. So that also I discussed in the last part of the session last time. But here's the thing. See, there are certain very obvious limitations when it comes to the binary coded genetic algorithm. So if you want to have more accuracy for your solution, then you will need to have a very lengthy string. Means, let's say you want your solution to be 1.0000, like least count of your variable solution should be 0.0001. Then based on your encoding algorithm, it may require 11 or 12 elements in your string. So that is not, and if you have a multivariable, multivariable problem, then you multiply the number of variables to this particular 12 string. So it's a very big string or a chromosome or population that you have. Then you multiply with the population. Yeah, so it will be a very space consuming. So as you increase your accuracy, it becomes increasingly space consuming. And the lengthier the string means the higher the computational cost also. So these are some of the major limitations of this genetic algorithm. Sir also shared some more limitations, so you can refer to them. But let's stick with these two. And out of these steps, this first one is basically mandatory for doing the genetic algorithm in terms of binary coding. But let's see what are all the other steps that we were doing that actually required the encoding into the binary string. So only these two steps, like that is the crossover and mutation, actually required us to represent the solution in terms of binary encode. Otherwise, when we are doing the elitism, when we are calculating the fitness value, and when we are doing the selection operation, what actually we did was from the binary encoded value, we went back and got the real value and then did all these calculations. But only in the crossover and mutation, we directly use these binary encoded strings. So can we do this crossover and mutation without converting our variables into binary? So there has been research and there are several methods. So I'm going to all there is simple crossover, there is linear crossover, single arithmetic crossover, whole arithmetic crossover, and simulated binary crossover. So all these above four are pretty straightforward. So we will be discussing using our for our example problem. We'll be y- yes, Mr. Prasad. Okay. Okay. So yeah, so for our example problem, we will be using this simulated binary crossover. Rest of the things you can refer from the video. It's pretty straightforward, so I didn't want to spend time on that. So basically, here you see xi1 comma t. So the 1, that is the x coordinate of this particular location, represents this is the one of the solutions, and the first parent, and this is the second parent, and t represents that it is the like tth generation, and t plus 1 here represents that is the next generation, that is these are the childs that we obtained from doing the crossover between these 1 and 2 at the tth time point or the tth generation. So basically, we have u, a random variable, and nc, a parameter that controls how far or how close these variables, these new childrens that we are going to get, are going to be from their parents. So if here is a quick table if else loop you can apply in a code, and then you can get the value of beta, which is then going to be used to calculate the value of the new generation. So u is a random variable that you can generate using the uniform distribution random variable, and between 0 to 1. If it is less than zero point 0.5, then this is the value of beta. If it is greater than zero point 0.5, then this is the value of beta. When you look at this, why we said that NC is the parameter that actually, you know, defines how close or how far these children are going to be from the parents. We said that because when NC is very high, let's look at this expression. When NC is very high, this denominator is going to be very high, and then this whole 1 by NC plus 1 term, this term is going to be effectively 0, and anything to the power of 0 is 1. And when you put the beta equal to 1 in this expression, then what you see is for xi 1 t plus 1, you will get this term will be eliminated because beta is 1, and you will get particularly x1 t. So this parent is same as no, sorry, this child is same as the parent. So that's why we say that this particular parameter nc is going to determine how far or close these children are going to be from the parent. Okay, so we'll perform these calculations in our example problem. Then how can we do the mutation in the real coded variable problem? So then again there are two simple approaches. One is random mutation and another is normal random mutation. Random mutation basically is when you give a predefined range in under which your variable is going to be shifting, and then where it shifts, it is decided by the random variable. In normal distribution, you signify the standard deviation for the random variable that you are creating, and it is going to provide that perturbation to the variable. The interesting thing is the polynomial mutation, because it is similar to our previous simulated binary crossover also. So by the way, I should mention this. This was I think developed by an Indian scholar. So we'll be using this. You know, yeah. So polynomial mutation. So basically here your x1 t plus 1 is the child that you got after the crossover between the parents, and y1 t plus 1 is the mutated generation after introducing mutation. uh, Delta is calculated based on this formulation, so I think there was a mistake in the ppt. So the u again is the random variable, nm is another parameter that is going to, so I should put here mutation. I will change that. So nm is the parameter that is going to control the mutation, and when u, that is the randomly generated variable, is less than zero point 0.5, then the formula for this tilde or delta is 2u to the power 1 by n plus 1 minus 1. So this minus 1 that was by mistake shown in this power itself, it's actually uh, subtracted from this whole part. So once you calculate this, then you go and subtract the value with minus 1. Otherwise, you will never get the value of this tilde or delta as less than 1, and then you are actually biasing your mutation towards the higher end of your variable. So this is the corrected one which we will be using for our uh, example problem. So, and one more thing that sir discussed in this week was when we have we why do we use this genetic algorithm? Actually, we use this to get the global optima. But in if there is such a scenario or such a requirement arises that you want all the optima points in a function, then genetic algorithm is not going to be helpful as it stands now. As far as we have discussed, we will not be able to get let's say this point, because genetic algorithm is going to favor the global optima point. So basically, during your iteration, let's say you initialized, or one generation in your problem solving comes out to be these points, these red points. Then when you perform the fitness and selection, then the expected or the actual count of your these points. So since we have to conserve the size of the population, so initially we have five red dots. So after the selection process, we still need to have five red dots. So this this point will be doubled, this point will be doubled, and this point will be kept once, and these points will be removed. So that's how, uh, as far as we have understood genetic algorithm, it's going to work. But today we'll also discuss something that is called crowd filter, which will allow us to reduce the probability of these points, the global optima points, getting selected more based on a predefined distance between the accepted solutions. So let's say we predefine this sigma limit that we will have. So we want to say that two solutions should not be, when they are the distance between these two solutions is less than this sigma, then what you do is you try to reduce their probability of selection, so that less number of those solutions will be selected. And when we do that, we are automatically increasing the probability of other solutions getting selected. So this kind of process of crowd filter, I am calling it crowd filter. I don't know, I forgot what it is actually called. So yeah, we'll be using for the multimodal genetic algorithm. Now what I will do is, let's try to solve this particular problem using the real coded genetic algorithm, and let's try to do one or two iterations and try to understand where we shall apply this kind of elitism and other steps that we discussed. So what I will do is I will be sharing my screen of this, or maybe let's use Excel. It will be easier to apply if and else conditions. So we'll be using Excel. Okay, so let's use this Excel. So let me increase the size so that you can also clearly see. So is this fine, Mr. Prashant? Is this audible, like visible? This X and FX clearly visible? Uh, you don't need to speak. You can just chat. In chat also you can put okay. Otherwise, in the end, it shouldn't be a problem. Okay, so let me check in some other screen. I think this is fine. Yeah. Yes. Okay. Thanks. Yeah. So we have a function. Okay, let me just show the function again so that you can also write and you can also work it out in hands with me. So we have a function x into cos square x, and we have to find. We will do two or one or two iterations for this optimization unit using genetic algorithm and real coded method. Okay. So the range is from 0 to 5, and I can see that the function is always positive in this particular range. So that will, you know, and we have to do maximization. So that is going to motivate me to use a particular fitness function. That is, I'm just writing it as rough here. Fx will be equal to fx. So the fitness function, actually I am putting it as equal to the value of that function itself. So I don't need to trouble myself. Now, so straight away when we are doing in real coded, we don't need the precision step. So we don't need to define our precision, and we don't need to select the length of the string that we are going to use. So let's just start with the step 2 for my case, and that will be guessing the initial solution. So let's take some value that is between 0 to 5. Let's take 4 value for our simplicity. So let's take 0, 1, 5, 4, 3. So I'm taking 5. Okay, let's take 5 itself. Now let's compute the value of. So this is our initial population. So we have actually done step 1. Step 2 is the fitness fitness calculation, right? So let's calculate the fitness. This is x into cos x square. So this is our function. Let me. This is step 2, but this particular value is fx. Fitness, and my fitness function is actually same as this, so I will just copy this here. So this is my fitness value I have calculated here. Now let's okay, let me write here. Maybe let's keep it as a sub step, because this one we will be using for our elitism. 1b, let's keep it as 1b. Okay. Now let's what we should do is we should do elitism. Is that the correct step? Let me just cross check. So yeah, we have calculated the fitness, and then let's do the elitism. Yes. So let's then make it step 2 itself. Elitism is selecting the best solution that we have and transferring it to the next generation without any mutation or crossover. Okay, so that's what we have to do. So for that, let's see which one we should select. So this particular value of x, that is 3, is giving us the highest value of this fitness function. So let's take x equal to 3 for that. And let's choose only one for now. X equal to 3 is chosen for elitism. Now let's go ahead, and probably I didn't mention here is we'll also be doing the crowd filter. So between this after this elitism, or before and after, and before this selection, we have to do crowd filtering. So that is to just modify this fitness value as discussed in the video. So let's do that. Step 4 is crowd filter. So here's the interesting part that I think one should keep in mind. See, when you are here, you have this particular iteration, and you want to do crowd filter. So you have to actually use this particular value that you have, that the best value, or should I say the value chosen in the elitism, also when you are doing the crowd filtering, because if you don't choose that value and you try to do the crowd filter, then these probability of these things will not be reduced as much as they would have when you are doing the crowd filtering. So you will see what I am trying to explain when we go with this. So we have to do crowd filtering. So for that, we have to first calculate the distance between each consecutive points. So let me just write here x, and how many points we have? We have 0, 1, 4, 1, 5, 4, 3. So we just copy paste them here and copy paste them here. Then the distance between these 2 points. So it will be a tedious process to compute the distance between all these like manually, because if I drag down, I have to put dollar signs everywhere. So what I will do is, let me just in the process of crowd filtering, we have to define a parameter called sigma, uh, which will be the threshold that we will be using for the minimum or distance between two solutions. So let me just define it straight away here, and I will write it at this particular place. I will write the distance when we see that the distance is actually greater than this particular value 1. So we have here distance 0, so let's leave it at that. Okay, so I will write the distance when this particular distance between these 2 points is greater than, sorry, less than this sigma. Yeah. So this distance is 0, and this distance, so this distance particularly is between 0 and 0. So let me highlight this by doing this. So we have to calculate the distance of each member of this population with each other, with all the possible combinations. So 0 will be checked with 0, 1, 5, 4, 3, 1 will be checked with 0, 1, 5, 4, 3, everyone. So this one is simple. So this particular distance is 1, this one is higher, this one is higher than 1, this one is higher than 1. So we leave it at that. This distance between 1 and 0 is 1, and this is 0. Then this is higher than 1, it will be 4 here, 3 here, and 2 here. This will be higher, it will be 5, 4, then 0, and then it will be 1 here, and it will be 2 here, so it will be higher, and this will be 4, 3, and then 1. So when I say distance, I am assuming by default that you know that distance is positive, so we are going to actually use the absolute of this minus this. So for this particular value, let me just write it for once. So let's say this value, it's the distance between this and this point, so it is equal to absolute of this minus this. So yeah, so we get 1. So like this we have to do for everything. Okay, so as we proceed, so the distance between 4 and 4 is 0, 4 and 3 is 1, 3 and 0 is 3, 3 and 1 is 2, then 2 and 1 and 0. So this is my distance table. So any doubt in this particular step? Okay, so see, if you have, since you are not speaking, so what I will suggest is you can do this. Since if you have a doubt, you raise your hand and then you start typing, so that I will wait till you type and then we can discuss. Okay. So otherwise, if you are typing now, I won't know and I will proceed, and then I will have to come back and all those things, right? Okay. So then when we have calculated the distance, then we have to calculate the value of sharing function. So if you remember in class, from the class session, sir told that when the value of this particular distance is greater than your sigma, then you write your sharing function as 0, and when your value of this distance is less than sigma, then you write it as 1 equal to the 1 minus distance by sigma. So let's do that and let's calculate the value of sharing function. So here our sigma is 1. We have decided here. You can decide any value based on your choice. I have decided here 1. So when our d is less than sigma only, I have written these values here. And when you look at it carefully, what you will see is when your d is 1, that is this distance, your the value of your sharing function is 1 minus d by sigma. So is 1 minus 1 by 1. So every 1 here will be transferred to 0, converted to 0, and every 0 will be converted to 1. So let's just do that. Okay, I should have probably done this. Okay, so uh, is this clear till now? Okay, yeah, thank you. Yes. Now what we have to do is we have to calculate the niche count. I don't know why they call this niche count, but that is it. Niche count we have to call this. And niche count for a variable 0 is the sum of these things. And basically one more thing I forgot to mention, that I didn't write the value for distance when it was greater than sigma. You can clearly see that this will also become 0. Your Let me copy it and paste it here. Your sharing function value itself is becoming 0, so that's why I didn't write that. So you can just put it here 0 0 0 if you want. I will just put it blank. So the niche count actually for this particular variable 0 is the sum of the sharing functions for uh, for this particular function with all the, for this particular solution with all the other solutions. So when you add it, it will be 1 plus 0 plus 0 plus 0 plus 0, basically 1. So as it stands for our first iteration, we actually do not have any, we have a kind of a uniformly distributed solution. So we do not have to do any kind of change in the fitness value before the selection. So everything when you add, it will be 1. So let me just write that. So we have this niche count as 1. Okay. And still we will do the step, that is this step 4 of crowd filter. What that crowd filter does is it modifies the so yeah, it modifies the fitness value. So let me just write here old fitness value, and then modified fitness value for our, and how do we define this new fitness value? New fitness is nothing but old fitness divided by the niche count. Let me write it as NC, niche count. Yeah, I cannot put it equal to, yeah. So this is the formula for new fitness. So let's just copy the value of our old fitness and paste it here. We have to paste it as values, otherwise it will be creating some problem. And this is this divided by 1 for our particular this scenario. So new fitness is same as the old fitness. So now that we have done all this crowd filtering, which was ineffective for our particular iteration, we proceed to the step 5, that is selection. So notice that even though I had done this step 3 elitism and chosen x equal to 3, I am not actually removing it from this kind of you know what should we say, crowd filtering. I will not modify the value for this particular variable. Okay, so it will be better if I write it like this. I will not modify the value of this variable, but I will use it to identify the crowding. So this particular thing will not be modified, but we will still use it. So what is step 4? Oh, sorry, step 5. Step 5 is selection. So let's go with the selection. So we have x and fitness value, and then we do the sum of these values. Okay, so now we will remove this. Now we'll remove, because we have you also have to remind me later on that we have performed an elitism for this particular variable. So we have to remove this from the selection, because we have already selected it. So our solution number of solutions in our population is 1 2 3 4 5, so it will be 5 in the end also, but this will be automatically there. So let me just red mark it and not use it in our selection and other processes. So the we have to normalize this fitness value for the relative fitness. So let me just do this. For normalization, we have to do the sum of these particular values, and the relative fitness, or RF, for this function will be the fitness value divided by the normalized fitness. So let me just put dollar so that it is same for all these things. So we have our relative fitness values. Based on this, so there are again several methods for selection. I like to use a simple method, that is just based on the multiplying this relative fitness with the number of available positions in our new generation or the new solution. For this case, we have only 4 because we have already booked one for the 3. So the expected count, that is EC, is nothing but this relative fitness multiplied by the available number of positions in your new population. So since we have already given one position to 3, so we have only 4 left. So this is your expected count: 0.48, 166, and 2.84. So since we cannot have fractions, we have to do some approximation where this will be 0 and this will be rounded out to 0. This will be rounded up to 1 and this will be rounded up to 3. So now we have, after the selection process, we have these two left, and this is again sent to the uh, next generation by itself. So, and in this thing, in this, after the selection process is complete, we have 3 copies of this 4 and 1 copy of this one. So this can create some kind of bias, and our mutation will try to rectify this problem using the mutation. So let's do step 6. That is, now we have to do the crossover to create the children. And which method did I say we're going to use? We'll be using simple binary crossover. That is this one. So let me just keep it for my reference so that I don't make any mistakes. So what do we have after the selection process is complete? We have these two variables with us. Okay, we'll paste the values. And we have to get, for our new population, since we have to conserve the number of solutions in our population, that is 5, we have to get 4 more solutions. So don't be afraid if you see that there is being a repetition. We will The mutation is going to help us with that. So two childrens we will get from 5 and 4, crossover between 5 and 4, and 2 childrens we will get after crossover between 5 and 5. It will be no matter how what procedure we are going to use, when these parents are identical, the crossover actually, for the method we are going to use, it is going to produce the same output, 5 and 5. So let me just write it like that, and we'll cross check it also. But let's use 5 and 4 first to understand how this crossover works. So, if you remember, let me just show you again. So, we have to generate a random variable between 0 and 1, and we have to assign a parameter NC that is actually going to give the decide how this crossover is happening, how far or how close these children are to their parents, and then we calculate beta using these two particular values, and then we go on and calculate the children. So just if you want to write, you can write. I will be looking at this, referring to this when I am coding it or putting it into the Excel. So let's say this is the column for you, and I decide that my NC is going to be. So as I mentioned that if your NC is high, uh, your offspring or your children of this particular solution is going to be close to your parent. So let me choose a lower value of n. Let me choose NC of 1. This also is a little bit high only, but let's just go with this. And let us create a random variable. So let me create it using inbuilt function in Excel. So this is a random variable between 0 and 1. So let's create this for the other crossover also. I'll just copy paste and it will give me different values. So you can just enter. When you press enter, it is always going to give you different values between 0 and 1. So then we have to calculate beta using this particular UA. So we have to use if loop. So I hope you are familiar with the if loop. If you have any doubt how to apply if loop in Excel, I have also discussed. I have spent some time in my previous videos. One of the videos where one of the participant had a doubt, or you can refer to YouTube for this. I'll be just quickly putting the if loop here. So whenever we are putting a function, we have to give an equal to in this sense. Equal to if a logical test, that is this one is less than or equal to 0.5, then our first condition. So when that was the case, then the condition was the beta is equal to 2 into u the power 1 divided by nc plus 1. And that was when, okay, that, that was when we had u value less than zero point 0.5. And what if it is not less than zero point 0.5? Then we have the other scenario. In that case, we had 1 by 2 1 minus u. So 1 divided by 2 into 1 minus u, and this whole thing is in the denominator, then to the power 1 divided by nc plus 1. I have forgotten. Yeah. So this Excel automatically corrected. I was forgetting one bracket. So you will get the value of beta using this. So maybe you can refer back to the video, or if you think I have done any mistake in this particular beta calculation, then you can tell me now itself. I'll just show it here and put some dollar sign for n so that it doesn't change the value of n. So if this is fine, then this is the value of beta we are getting, and I will just copy paste for this, and it is going to use this particular u. So what will happen when I am going to press enter anywhere? This particular u is going to give me new and new random values. So let me just calculate the use this value and calculate the value of our new generation. So for that, I will just put it here as a paste value so that I don't have to refer to the changing value again and again. and then let's just change their color to red so we don't confuse. This is the beta that I have chosen, and the new population, the first one, let's say using this, is 0.5 into 1 plus beta into the first parent plus 1 minus beta into the second parent. Is this clear? And let me just put some dollar sign so that when I copy paste this here, it doesn't change. So for this, actually the second for the second population, you just swap these two things and then you will get a second population. So for the first population, this A54 was multiplied with 1 plus beta, and here you will see that A53 is multiplied with 1 plus beta, and that's what actually was shown in the PPT also. So you can see, if you want to get the second population, you just swap x1t with x2t and you will get the second population. And that's what I have done in the Excel. So here are the two new populations using this particular thing. And just for the, for the sake of it, I will do that for this also, and you will see that we are actually getting 5 and 5 no matter what we do. So if I just copy paste this here, you will see that it is going to use that. Yeah, and just copy, bring this value down here so that it doesn't confuse us. So now you see it is using this particular value of beta and using these two parents, and still no matter what beta you give, it is going to give the same answer. Yeah, so I have to just swap these two parents, and you will see that no matter what your beta is, if both the parents are same, the childrens are going to be same. Okay, so here's one thing that can happen in while doing this crossover. Let's say I use this value of beta. So do you see any problem in this particular solution? There is a problem. I just want to know, can you identify this problem in this solution? If you don't see any problem, then you can type we don't see, or you can say we don't see any problem. Okay. So the problem. So Mr. Prashant, you don't see any problem, right? So actually, there is a problem with this solution. That will never happen in case of binary encoding. I will tell you the problem. Look at this question carefully. So the question that we gave, if you look at it carefully, it's a very simple problem. Like we will miss out. It's that kind of problem. Look at this question carefully, and notice on this part. Do you see this? This signifies the range of our search. We have to stick between 0 to 5. But when we are using real encoded, and we are doing the crossover using some random value and some formulation, what we are getting? We are getting a member of this population who doesn't belong in this population. We are getting some higher value. So there is a little bit of a additional step that I think we may have to include in our genetic algorithm case. That is, we have to check after this crossover that whether our all the members are within the population limit or not. Is that clear? So you just have to create another random variable, and when you do that, when you use different value, you will get back to the population. So kind of an if loop you have to put, where you check that if this population or this child is going outside my search domain, then I recompute for this child specifically how I have computed, and then I go ahead for the second child. Is that clear? Okay. So let's go with these children to mutate them. Sounds weird, but yeah, mutation. Have to copy it again. And the formulation that we'll be will we are going to use for this mutation is our polynomial mutation, and you can look at it again. I'll be seeing looking at this particular thing for reference, so that I don't make any mistake. Okay, so now let's do the mutation. For mutation, again we need random variable u and the characteristic parameter nm. So let me give value to nm as zero point 0.5. You see that these random variables keeps on changing. That's why I copied the value of beta and kept it here. Just put a constant also here, so that if you are looking at this Excel sheet later, you do not get confused. Okay. So we need u, and based on that we are going to calculate our delta or tilde. I do not know what we are going to call it. So again we create some random variable. Four random variables we have created, and then we are going to calculate delta using these random variables. Again, I'm going to use if loop here. So if this particular value is less than zero point 0.5, then my delta is given as 2 into this value to the power 1 divided by 1 plus this nm parameter that is pre-decided, and then whole thing minus 1. And if it is greater than zero point 0.5, then my value is 1 minus, so yeah, 1 minus 2 into 1 minus u to the whole power 1 divided by nm plus 1, and that's it. So we'll just put some dollar sign so that it is easier for me to drag down instead of changing the value. We have this value. So this, when minus comes here in this delta, then it kind of gives me relief, because your perturbation can happen to the left or to the right of your given value, and when delta is negative, then only that is possible. Okay, so now your y, let's call them y, the new generation after mutation. I need some minus value here, so let me just do it again and copy these and keep them here, and again color them as red, so as to warn that these values will keep on changing. So delta extent. So what was the formula for the new generation? It was old generation plus delta into the width of your simulation domain. So the higher value minus the lower value. So higher value for us is 5 and lower value is 0. So we'll just multiply with 5. This is the this is what we get after mutation. These are your 4 new children. Now the new generation. This is not a step, but let me call this thing as new generation that you get after doing all this process will include what variable will include the 3 that we had chosen during the process of elitism. So let me write. Okay, to put it as a value, let me give the 3 its place. So this is our new generation. And then again we go on throughout this process of again elitism, like crowd filter and all those things. And let's do that actually. So we have 8 minutes only, so let me just actually go till the point where we are doing the crowd filtering so that it is a little bit easier for you. Okay, so let's quickly do that. So is there any doubt till now? Then maybe we can try to rectify that, or else we'll move on and do the crowd filtering till the crowd filtering part, and after that it's just pretty straightforward. So shall we continue? Continue. Thank you. Okay. Yes. So we we calculate the fitness. We have our new generation. We paste the values here. We have our fx. That is, we just I don't want to write it. I will just copy this from here, and it will bring the associative relationship with the neighboring cells. So yeah, so this is correct. Just copy paste it down, and then you see that we have fx value and we have a capital Fx, that is our fitness value. And as I said, this is a maximization problem with all the possible values as positive. So my fx is my fitness value, and that we have here. Surprisingly enough, so even though we have used actually random values here, what you see is your 3 has escaped out again. So, but let's see, can we, let's go, still let's go to the, crowd filtering. So again, you see that 3, the variable 3 has the highest fitness value. So I'm just going to do the elitism, and I choose x is equal to 3 again. But for crowd filtering, let me still use it, and then let's try to see what is the modification in the values of the fitness values that we get. So what do we have here? We have these values, and we have these values here. And we have to calculate the distance between these values. So let me just uh, reduce their degree of significance, so it is easier for me to. Okay, it won't let me do for y, so it is easier for me to write. Okay, so the distance between, let's just first finish off the diagonal elements, and you remember my sigma, I chose it as 1. So I will only write the distance which is lesser than this particular value of 1, so that other values anyhow, when we are going to calculate the sharing uh, function, then it will be 0 only. So this is 0, 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 because the distance of this point with itself is 0. And when you look at this, it is going to be greater than 1, 2.86 minus 0.69. This is going to be greater than 1, greater than 1, greater than 1. So I will not write that. This is again greater than 1, 0, and this is a lesser. So it is 0.14, I think. And this again is lesser. So it is, let me just do this, 0.78. Okay. Do we have some kind of, oh, so since I have done a bit of least count manipulation, I am getting two members as same. But let's see what we get when I do the subtraction. Yeah, so Excel in itself remembers that these values are different, so no need to worry, it is still giving us the different distances. Okay, so this distance between 3 and 0.69 is greater than 1, we will not worry about it. This is 0.14, and 3 and 3 is 0, 3 and 0.64 is 0.64, then this is, so it's actually 0.63, right? So let me just write 0.63, 0.64, and this value we can ignore. This value we can obtain from here because this is kind of a symmetric thing. 0.78, 0.63, and 0.01. Then this is again 0, the distance between these 2 points. These 2 points is 0.79, 0.64, 2.01, and 0. Is this clear till now? Okay, thank you. So now we have our distance functions. Now let's calculate the value of sharing function. So I will be using a loop for this. Okay. Yeah, you see here it is automatically giving us a more clean result. Okay. So let me just put these values here, that if equal to, so as I showed here, let me copy it and paste it. When your distance is greater than sigma, then your the value of your sharing function is 0, and all these empty brackets the sharing function is 0, and only these places we have to calculate the value of your sharing function. So this value of sharing function will be equal to 1 minus this distance divided by sigma. Since my sigma is 1, I will just leave it at that, and I can just drag it, and it will, I think, do that operation. Yes, so it is doing that. So I can do this for all the values here. Very good. And this is left, I will put here 1. So is this clear how we calculated the distance? It's just nothing but this particular value is 1 minus this particular value divided by sigma. Okay. So now when you have this uh, distance, let's go ahead and calculate the niche count. Niche count, as I mentioned earlier, it is nothing but the sum of all these values. Since these are 0, it doesn't matter if I leave them here or leave them empty. So here you see we are getting some niche counts. Previously we got 111, but this time we are getting some good values of niche count. So now what we do is we modify the fitness value of the solution members in the solution. X hold fx and new fx. Let's call it f dash, no, f1x. So this is my solution. But you remember that I have chosen this earlier itself for relatism, so I will not be doing anything with this one, but I will be changing the fitness value of other variables. So this new fitness value is old fitness value divided by the niche count. So I will give this particular value here, and we don't see any difference because the niche count is 1. And we drag it down. We just remove these. Don't mind these values. So we see now the crowd filtering is done, and from 3, so this would have been approximated up to 3 or something. This the crowd filtering has reduced the fitness value to 1, right? So this is uh, very good for us to get the modal solutions, all the possible point of optimum. So let's just actually go ahead and perform the selection also. So this is your f of x, sorry, capital F. And when you want to calculate the relative fitness, you have to do the sum. And relative fitness is nothing but this divided by the total fitness, summation of all the fitness values. Okay, so we have, oh, okay, I should put here dollar, otherwise it's going to drag down that. This is our relative fitness. Again, we have four places left for the new, the selected members. So we have to do expected count is equal to just relative fitness into 4, and what you see here is, so there is an issue. What issue we are currently facing is when you round them up, you will round this down to 1, 1, 1, and this will be rounded down to 0. And but we actually have 4 places in our solution, right? But if you just use simple rounding method, then you will only get 3 because this will be rounded down to 0. So what you can do is you will have to add a fail safe, and that is probably there in the genetic algorithm, which will increase the count of the highest expected count by +1 if you are missing the uh, one value or two values in your actual count. So let me just round this up to 2. So this will be my selected member for crossover. So let me just put this here as values. We have this, and then we'll do the crossover. So let's say I want to do the crossover of this with this and this with this, so that we have a difference in the solution space. So is this clear? I think we are also past time. Then crossover and mutation is just a simple process. Then again we introduce our 3, and then we see if there is someone better than 3, so that the 3 can be introduced into the process of all these selections and mutation and crossover. We keep on going, and that's how we will get the genetic algorithm. We do the genetic algorithm in the real coded slide. So if is there any doubt, or if not, then probably I think that's time we should we'll end the session today.